So smaller particle accelerators are interesting because if, for example, you want to treat cancer, that needs a much lower energy particle beam.
Radiotherapy is one of the ways of treating cancer. About 40% of people who survive have radiotherapy as part of their treatment. This can either be done by X-rays, protons or brachytherapy. With brachytherapy, it's delivered directly to the tumour. With X-rays, it's delivered through the tumour, and with protons, it's delivered in a peak that coincides with where the tumour is.
A LINAC, a linear accelerator that we use here, is the medical LINAC. It's a device which uses like high energy radiation to treat cancers, so it's MV radiation.
So this produces microwaves, and instead of going into the oven, they come along this part, they travel out here and they go up, bounce there and go bounce backwards and forwards. So these are going positive, negative. The electrons get injected in, and when this goes positive, the electron gets accelerated. When that one goes negative, this one goes positive, gets accelerated again. Now the electron then hits the target, and these will give us 6 MV of X-rays that we want.
One of the biggest advances in radiotherapy in recent years has been that we now try and conform the dose to the tumour. So what we're trying to do there is put the maximum damage into the tumour and the minimum damage into the surrounding healthy tissue, because that's what normally causes the side effects. If you're thinking about the differences between X-rays and proton radiotherapy, X-rays deposit their dose, they come in and they deposit their dose in a broad peak, whereas protons deposit their dose in what's called a Bragg peak. We can change the energy, so we have what's called a spread out Bragg peak, but it's the way in which the energy is deposited. With protons, you don't have any exit dose, which means it's great for treating tumours that are close to a critical organ.
A medical linear accelerator is a machine. It weighs about 6 tons, and it's able to generate and deliver radiation to target volume inside a patient, and it can rotate around the patient and deliver that radiation from different angles, always concentrating on the target volume.
Behind me we have a proton beam therapy system. The beam therapy system comprises of, first of all, a cyclotron, a lot of magnets, so quadrupoles and dipoles, that are used to bend and used to focus protons, and then we need to be able to move the actual proton into the patient plane. A cyclotron is a device used here to provide protons that are used to be able to treat tumorous volumes within patients. The cyclotron itself has a fixed energy, and due to that we have other devices along the beam line that are used to change the energy of the protons themselves, so an energy selection system which allows us then to paint tumorous volumes in the patient.
In the UK, 40% of patients who'll be treated are children. Obviously, if you're treating someone who's 10, who's got very sensitive organs anyway, secondary malignancies in 30 years' time are going to be of major importance. Whereas if you're treating someone who's 70 or 80, they're probably not that worried about what might happen when they're 100 or 110. We're also looking to treat with protons in adults tumours that are difficult or impossible to treat by more conventional means. So we're picking those tumours where there's most chance of using the efficacy of protons.